During the last lesson, we have described the effects of the non-steroidal anti-inflammatory drugs. Now we'll see the chemical structure of the different families of this important group of drugs. From the historical point of view, you see the first family is represented by salicylates, in particular salicylic acid. It's a natural compound, but you see a lot of other compounds in the same class. Other classes, aryl alkanoic acids, aryl propionic acids, antranilic acids, oxycams, the most recent class, and then COX-2 selective inhibitors. Here you see once again chemical classification of the different anti-inflammatory drugs. And it is important to note that all these classes are characterized by an acidic function. Why? Because if you remember, on the rim, at the beginning of the tunnel of cyclooxygenase 1 and 2, there is arginine 120, a basic amino acid, able to give a strong interaction, an ionic interaction with arachidonic acids, and also with all these inhibitors. So it is necessary the presence of an acidic function if we want to have an interaction with cyclooxygenase. Once again, you see the chemical structure of arachidonic acid. You see the 2-cyclooxygenase 1 type constitutive present in stomach, intestine, kidney, platelets. COX-2 indocible, but also constitutive. And you see where it is located, where they are located in macrophages, endothelial cells, and so on. Please remember the most important severe side effect, which is the attack of these drugs to the parietal gastric cells. And also, these compounds are able to block the biosynthesis of the protective film necessary to defend the gastric cells from hydrochlorhydric acid. I remember you, in stomach, the pH is about 1.5. First family. The prototype of the first group of this type of compounds is salicylic acid. Very simple structure. Aromatic ring, acidic function, OH group in ortho position. Salicylic acid is a natural compound, but can be used only topically. Why? Because salicylic acid is too hydrophilic. It is not able to cross any membrane, you can see the acidic function can be ionized, and so you have the charge form. And then there is also another OH group which increases the hydrophilicity of the molecule. This means that salicylic acid can be used topically, perhaps on the skin. In particular, if you have this type of problem, I don't know the name in English of callo, I don't know. But it is, okay, against leaks and warts, you see. You can use a plaster with the salicylic acid inside, and you can apply the plaster directly your foot fingers, and for corn, this is the exact name. Because salicylic acid is acidic, and so can attack, can disorganize the stratum corneum of the skin. It's not a strong acid, so can be used topically without any problem. See, yes, because it is able to, it has also a peeling effect on the skin. You can clean the skin, and so you know the acne sometimes is due by the occlusion of particular pores of the skin, and so you can clean the skin with the salicylic acid. Normally, you can use weak acids, natural weak acids, and salicylic acid is weak. Yes. The strategy in the past was to increase the lipophilicity of salicylic acid. And so you can see two derivatives more lipophilic, which are acetyl salicylic acid and methyl salicylate. You see methyl salicylate at the first. And how the lipophilicity was increased? If you see the acidic group, the carboxyl group, is esterified with the methyl alcohol, very common reaction. You get methyl salicylate, which can penetrate through the skin and can have an anti-pay and an anti-inflammatory activity directly on the injury. So methyl salicylate, you can find this compound in all the creams. But the most interesting compound is acetyl salicylic acid. Also, this compound is characterized by an ester function, but in this case, the ester function is on the OH group and not on the carboxylic group. Acetyl salicylic acid is a milestone compound of this class. As I told you before, it was synthesized together with heroin. In that time, a German company had a lot of acetic anhydride, and the company decided to use generally to apply an ester reaction to a different compounds, heroin, acetyl salicylic acids, and other. But without any, can say, any goal, any medicinal goal, just because we have a lot of anhydride, acetic anhydride. But really, they discovered a very interesting compound. We'll see the mechanism of acetylsalicylic acid on cyclooxygenase. It's the only compound able to give a covalent block of this type of enzyme. There is another interesting compound, diflunisal, you see here. You can see the same backbone of salicylic acid, but to increase the lipophilicity of this compound, another desubstituted aromatic ring was inserted on the first benzene ring. You see also two fluorine atoms on the second aromatic ring. Normally, if you remember, fluorine has the same dimension of hydrogen atoms, the same cloud, but the effects are completely different. And these two fluorine atoms are able to increase further, to further increase the lipophilicity of this compound. So these are the four main compounds of this class. What about acetylsalicylic acid? It is the most important of the class, the prototype, the best seller. A lot of tons of this compound are sold every day in the world. In USA, with $5, you can buy 100 tablets in drugstore. But if you remember, the commercial name of this compound is aspirin. This name derives from the letter A, from acetyl, and the spirin. Spirin is the old name of salicylic acid extracted from spirea. Spirea is a plant common on the beach. And so aspirin derives from acetyl and spirin. Why? Which is the mechanism of action of aspirin? A moment, I show you on the can draw. Okay, I share the screen with the student at home. Okay. We can draw. Okay, here we have an oxygen. Here we have an OH. Here we have this compound, So we have an oxygen here, another oxygen here, and then we have a methyl group in this position. Okay. Which is the mechanism of acetylsalicylic acid? This is the tunnel of a cyclooxygenase. If If you remember here at the beginning, we have arginine 120. And so at the beginning, we have the interaction of O minus with the protonated nitrogen atoms of arginine 120, and then we have the normal ionic bond. But there is another important point. In the middle of the tunnel, there is another important amino acid, serine 520, which is characterized, if you remember, from an OH alcoholic group. This alcoholic group is able to give a nucleophilic attack to the carbonyl of the ester function. And so the result, the final result, is the formation of the acetylation of this OH. But why it is possible this reaction called transesterification? Because normally acetylsalicylic acid is stable. But please, you have to see the presence of the acidic function. There is an acidic proton very close to the oxygen of the ester function, the carbonyl of the ester function. This means that we have an intramolecular catalysis, acidic intramolecular catalysis. For this reason, it is possible this type of reaction inside the cyclooxygenase, and the result is to have an esterification of the OH of this serine inside the gauge, inside the tunnel. And so physically, this substituent is able to block the entrance of arachidonic acid inside the enzyme. We have a physical barrier. This behavior of acetylsalicylic acid, this intramolecular catalysis, is responsible of the low stability of this compound in solution. If you make a solution, water and methanol, for example, because aspirin is not soluble in water alone, you have to put a mixture, water, methanol, for example, If you make this type of solution, after few minutes, you will have the formation of salicylic acid again, and then acetic acid. So if you make an HPLC spectrum of the solution of aspirin in water and methanol after a few minutes, you can see the formation of the peak of salicylic acid, because aspirin is unstable in this condition. This is the reason because you do not find any liquid formulation of acetylic acid on the market. You can find tablet, you can find other forms, cream, what you want, but not drops. This is the reason. The instability in solution of acetyl salicylic acid by intramolecular catalysis, because the acidic group is in the right position, the right distance to give this effect. Have you any questions? Is it clear? Okay, Atom, have you any questions? Piyush? Okay. Then we share again the slide. Okay, you see here in the picture what I have already described, the ability of acetyl salicylic acid to acetylate the OH group of serine. In particular, in platelets, there is an important effect of cardioaspirin. Cardioaspirin is a formulation of aspirin in low dosage, low quantity, to prevent the formation of platelet aggregates, to prevent infarct attack. And you can take cardioaspirin for a long time. So you prevent the production of thromboxane A2. But this effect, the ability of acetyl salicylic acid to acetylate some nucleophilic groups, is also responsible of the non-specific acetylation on the protein surface. So it's possible the formation of antigen and to have the formation of antibodies. And so there are people allergic with a severe allergic reaction against against aspirin. It's a common allergy due to non-specific acetylation on the surface of the protein, and so our body is no more able to recognize this protein as own protein, and so we can have the formation of antibodies. Here you can see an X-ray structure, X-ray picture of, you see, salicylic acid in the active site, you see the OH here, and here you can see the acetyl residue on the serine 510, oh no, 30, sorry. So you can see the acetylation of the OH and the residue of salicylic acid inside the active site of cyclooxygenase. In particular, you can also see the bond between arginine 120 and the acidic function of salicylic acid. So we have a snapshot of the situation inside the enzyme. Another recent compound of this class is represented by diflunisal. The lipophilicity was increased by the introduction of a second aromatic ring. This compound is characterized by low gastroirritant effect. It is not able to acetylate the OH of serine because no ester group on its structure. No specific acetylation, and it is not effective as an antiplatelet agent. However, can be used in powder form. It's very effective against the pain, particular headache. One modification that can be performed on the backbone of salicylic acid is the introduction of an amino group in para position, para-amino-salicylic acid. This compound is no more an anti-inflammatory agent, but it is used as antitubercular against the Mycobacterium tuberculosis. So we have another type of effect. However, the OH group in ortho position can be replaced by an amino group, and we'll see this modification in the next class. It is also possible the introduction of a carbon atom between the acidic function and the aromatic ring. Homologation. It is possible to introduce a second carbon atom between the acidic function and the aromatic ring. Here you can see the different metabolites of aspirin. You see aspirin is here. Hydrolysis of the ester group, we have salicylic acid. Conjugation with the glucuronic acid. You see in particular on the OH in ortho position. Conjugation with the glycine. Salicylic acid is also able to form chelates with some metals. And also you can see the introduction of different OH, aromatic hydroxylation in different positions just to increase the hydrophilicity and to increase the elimination of this type of compound. Second class, phenamates. Phenamic acid derivatives. Phenamic acids. The modification in this class is based on the replacement of the OH group in ortho position of salicylates with an amino group. Why the amino group? If you remember, NH2 is an isoster of OH. So some years ago, the scientists tried to replace the OH, the ortho OH group, with the NH2 because it is an isoster. But if we introduce an NH2 in this position, we have an increase in hydrophilicity. So antranilic acid is not active as anti-inflammatory, is not able to cross the membrane. For this reason, another aromatic ring was introduced on an H2. And we have mefenamic acid, you see, meclofenamic acid, the same substitution, okay, with an aromatic ring with the two halogens. But the most important compound of the class is niflumic acid. Niflumic acid is characterized by a pyridine ring. You see the nitrogen instead of a benzene ring. Acidic function in ortho position, an amino group with an aromatic ring with a trifluoromethyl. A strong increase in lipophilicity due to the presence of trifluoromethyl and also by the presence of a second aromatic ring. Niflumic acid has a strong anti-inflammatory properties, anti-pain. It is used, it is very common, it's used to treat the infection of hair in the children, otitis, together with an antibiotics, Panacef, if you remember cefaclor. It is the classical protocol in the children with the otitis. I had 2 otitis with my children in the past. Both otitis on the last day of the year, 31 December. We spent 2 nights in the hospital, in the different years, with the 2 children in North Italy, in South Tyrol. And I remember very well the last year in hospital with my children, with a strong pain, yes, in the hair. So, niflumic acid and Panacef, this is the protocol. The Panacef is the antibiotic with the strawberry aroma, and so perhaps you know this type of antibiotics, very common. Okay, so third class, acetic acid derivatives. As I told you before, it is possible the introduction of an additional carbon between the acidic function and the aromatic ring by maintaining the same amino group in the ortho position. You see an H, second aromatic ring, but an additional carbon atom between the acidic function and the first aromatic ring. This compound is very common. It is called diclofenac. The commercial name is Voltaren in Italy, Voltarol. Okay. It's very common in my generation. I use this compound every day on my knee because I have a problem. This compound is very potent, but it is also very toxic in the stomach. It is very potent to block the formation of the protective film. And also, it has a liver toxicity. We'll see the formation of a quinone. We'll see, an aminoquinone with an ability to react with the active site of the liver enzyme. So it is very toxic orally. To avoid this type of toxicity, you can find a lot of different topical forms, plaster, creams, patch, what you want. It is important to use this compound topically to avoid general side effects. In the past, there were a lot of derivatives of acetic acid, but now no more, because they have a high liver toxicity. So for the moment, between the aryl acetic acid, aryl, you see the aromatic ring, aryl acetic, you see there is only diclofenac. You can please check.
No, if you want. No, you could just the patches. I want a question because usually they produce a sort of heat when you.
Yes.
But if you have an inflammation, why the heat is?
Okay. Warm. It's useful if you have a problem with the mobility. Okay, during the inflammation, perhaps no. But if you have a pain without inflammation, it is my case. Warm, it's very useful.
Yeah.
Okay. And but this compound is not able to create a worm. Normally, you can find capsaicin, peperoncino.
Yes.
This compound is able to give this effect. So they mix together capsaicin with this type of compound, put together, and then they make a cream, artiglio del diavolo. There are a lot of different preparations containing natural compounds with this anti-inflammatory. You can see the chemical structure of the compound of the previous class. You see the difference of the carbon atom in this position, the additional carbon atom here. But the chemical structure is the same. Toxicity of diclofenac. First of all, diclofenac is toxic towards because it is able to block the formation of the protective film in the stomach, of course. But also, if you see its chemical structure here, it's possible the introduction of an OH in para position here, you see, in paraposition, introduction of an OH, and the oxidation of the hydroquinone, oxidation to aminoquinone system. And so in this compound, you have an alpha-beta unsaturated ketone. If you remember, this compound can be attacked by a nucleophilic group present generally in the active site of the enzyme, in the liver, especially in the liver. So the formation of the aminoquinone is responsible of the toxicity of diclofenac at the liver level, hepatic level. Here you can see other metabolites represented by conjugation with glucuronic acids and with other compounds. Glutathione, for example, here you see. Glutathione is another important compound able to interact with aminoquinone. So glutathione can defend our enzyme system from these toxic metabolites. It is important that you know that the toxicity generally derives from the formation, from our metabolism. Because normally we think, we have this compound, it's not toxic, we can use, yes, but our metabolism can be able to modify a drug and to form toxic species. This is important. How we can protect our stomach when we are taking this class of compounds? Some years ago, a company had a good strategy to use an anti-inflammatory compound in a safer condition. In particular, they thought, yes, we can assume diclofenac, for example, orally, together with a prostaglandin derivative, PGE1. This PGE1 is an agonist on the prostanoid receptor. So this analog of PGE1, a stable analog of this type of prostaglandin, because I remember you, prostaglandin are not stable. But in that time, this company had a stable compound of PGE1. So the strategy was, I use an anti-inflammatory agent, a potent anti-inflammatory agent, yes. This compound is able to block, to inhibit the formation of the protective film, yes. But if you put together an agonist of the prostanoid receptor in stomach, we can restore the formation of the protective film. Very smart solution. In particular, you see here misoprostol. You can see the backbone of a prostaglandin. This strategy in that time was really smart, but there was a problem. PGV1 is a prostaglandin able to increase the contraction of uterus. It is used to induce the parting. And so some people in that time use this compound for illegal abort. For this reason, this compound was withdrawn from the market, and now it is necessary a prescription by medical doctor. So the idea was really smart, but the application not too smart. And so now you can find this compound in a pharmacy, but it is necessary the prescription of the medical doctor. We have seen aryl acetic acid derivatives. The prototype, the most important, is diclofenac. And now we have the hetero-aryl acetic derivatives. Hetero means heterocycle. Instead of a benzene ring on the acetic acid residue. Here we can find the most potent compound of the class. But as you told you before, most potent means also most toxic. The first, most important, the prototype of the class is indomethacin. We can see the chemical structure of indomethacin. There is an indole skeleton, indole residue, instead of the aromatic ring. Why indole? Because some years ago, scientists found in the urine of patients affected by different types of inflammations a lot of metabolites of tryptophan. If you remember, the chemical structure of tryptophan is characterized by the indole ring. And so they decided, in that time, they didn't know the chemical structure of the cyclooxygenase. And so they decide to synthesize, to introduce the skeleton of indole instead of the benzene ring. And in addition, if you see another aromatic ring with an amide group. If you see the chemical structure of indomethacin, you see that we have a free rotation of the bond between the amidic bond. So we don't know which is the active conformation of the indomethacin. Okay, we have a flat portion represented by the indole residue, and then we have free rotation of the second aromatic ring. So we don't know the active conformation of the indomethacin. In particular, we don't know if the active site, the cyclooxygenase, the The second ring is located in the same position of the other aromatic ring in the indole system, or in the opposite part. To solve this question, this problem, scientists decided to introduce a double bond, alkene, instead of the amidic bond. You remember, if we have a double bond, we can have cis and trans configuration, blocked. No more free rotation around the double bond. In this case, we can have the cis isomer, where the second aromatic ring is in the same part of the first aromatic ring, or the trans configuration, when the second aromatic ring in the opposite part of the first aromatic ring. The scientists found that the cis compound is the most effective, most potent, and so they synthesized sulindac. Sulindac is an analog of indomethacin, but the amidic group is replaced by a double bond group, an alkene group, and sulindac is the cis isomer. These two compounds are the most potent compounds of the class, of the entire class of the anti-inflammatory agents, but with a severe side effects, in particular hematopoietic reactions. There is another important point to underline: the presence of a sulfur atom, oxidase, a sulfoxide atom, on the chemical structure of sulindac. Why it was introduced a sulfur atom on this type of structure? Sulfoxide is reduced in vivo by our metabolism to sulfide. So we have the elimination of the oxygen. Perhaps here, just a moment. Yes. You see here sulindac, and after our metabolization, you see the sulfide form. Sulfide is the active form. But why sulfide is important? Sulfide is an excellent radical scavenger. If you remember, sulfur has a lot of electrons. It is able to give electrons to the radical species. And if you remember, in the area of injury, of inflammation, there is a strong production of free radicals. The reaction of the formation of prostaglandin is a radical pathway. So if we introduce a group able to block the formation of free radicals, we can have an additional anti-inflammatory activity in addition to the inhibition of cyclooxygenase. So this is the reason why you can find a sulfur atom on the chemical structure of Sulindac. Here on the top, you see also the two conformations of indomethacin, but cis-like and trans-like. I remember you free rotation around the amidic bond, and so with the Sulindac, the scientist found the right active conformation, which is the cis-like conformation. Scientists try to minimize the chemical structure of indomethacin. In particular, you can see tolmethine. Just a moment, here. Here. You can see tolmethine. You see the pyrrole group, this heterocycle, very similar but present in the indole system. Here you can see another aromatic group with a ketone, also present in the chemical structure of indomethacin. So the scientists try to minimize some chemical features present on the chemical structure of indomethacin. And tolmethine was the result. Here you can see indomethacin inside the cyclooxygenase. You see this is the indole ring, in blue the nitrogen. Here you see the acetic acid chain. The carboxylic group interact with the arginine 120. Here you can see the second aromatic ring with the amidic bond here. So we have the snapshot of the crystal, form of indomethacin inside the enzyme. Sulindac, we have already explained the importance of the sulfur atom, the active form. Here you can see some metabolites. In particular, you see the active metabolite after the reduction of the sulfoxide to sulfide. Etadolac is not important. Ketorolac. We have seen the minimized structure of tolmethine. Once again, the scientists tried to apply the frozen analog approach. In particular, they tried to block the free rotation in the space of the acetic group. They insert the chain, the carbon atom present on the acetic group. They insert this carbon atom inside another cycle. This system, characterized by two rings, 5-member rings, with a nitrogen in the middle, is called pyrrolysine. So pyrrolysine represents a frozen system of the acetic chain, acidic acetic chain. Why this compound is so important? Ketorolac represents the border between the anti-inflammatory drugs and the opioids compounds. If you have a cancer patient with a strong pain, at the beginning, normally, the protocol asks to use this type of compounds, particular Toradol, because you know, no inhibition of respiratory centers, no dependence, no tolerance. So at the beginning, the medical doctors try to treat the pain with the ketorolac. After, when no pain relief resulted, they have to pass to the class of opioids. So ketorolac represents the border between anti-inflammatory agents and opioids. It is interesting, the application of the frozen analog approach you see on tolmetin. Okay, now we have a synthesis, but we take a coffee. Okay. 15 minutes, 20 minutes of break, and then we have this synthesis, okay? Have you any question at home? No?
No, Prof.
Okay. 15 minutes break. Okay. Okay, we start again. We have a very easy synthesis. It's not difficult. You see, yes. Okay. So, can draw as usually. As usual, qua, nuovo. Okay. Perfetto, we have to share just a moment. Aspetta che volevo far vedere un attimo. Ok, perfetto. Upsala. Arriva. Ok. Ora se vediamo bene una cosa. Momento. Che sei qua. Ok. Arrivo. Qua. Ok. Ups. Questo. Okay. We have to synthesize diclofenac. The problem is how we can introduce these, the side chain. The starting point is represented by this compound. Without the side chain. The first step is the reaction of this diphenylamine, you see, two aromatic rings on a nitrogen. We make a reaction with this derivative. A moment. This compound is called oxalyl chloride. This compound is the activated form of oxalic acid. You have already seen oxalic acid in biochemistry. You remember Krebs cycle, if you remember. Oxalic acid is a natural compound it is a dicarboxylic acid. We can use its activated form we can treat oxalic acid, okay, with thionyl chloride, but the oxalic chloride, it's commercially available, so we can use it directly. What happens now? We have two carbon-activated carbonyl compounds with a partial positive charge, if you remember, because we have the halogens, the two chlorine atoms, more electronegative, and so we have an activation of the carbonyl. And then we have a lone pair, the nitrogen, and then we can have an attack directly on one of the two carbonyls to give this compound. Just a moment. Facciamo così. Ok. Così, così e così. Facciamo così. Avviciniamo questo qua. Facciamo così. E lo mettiamo qua. Togliamo il lone pair che non ci serve più. Okay. So we have the formation of an amide between the basic nitrogen and the oxalic acid, activated oxalic acid. Now we can close the cycle by an intramolecular Friedel-Crafts reaction. If you remember, Friedel-Crafts reaction are performed with a catalyst, aluminium trichloride normally, and we can have the acylation of an aromatic ring. In this case, in presence of AlCl3, we can have the closure of the cycle. We see what happens. Ctrl-C, Ctrl-V. So we can have this type così, 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 così qua. If you see, we have the formation, we have the ring closure with the formation of this dicarbonyl 5-member ring. We have two carbonyls. The first, but they are different. The first carbonyl is an amidic carbonyl And the second carbonyl is a ketonic, a ketone. So the two carbonyls are different. The first one has a completely different chemical behavior than the second one. It is possible to reduce only one of the two. It is possible to reduce only the ketone carbonyl and not the amidic carbonyl. How? We can use the name of the reaction is Wolff-Kishner. This reaction uses hydrazine, sorry, due, is able to use hydrazine as reductive reagent. Once again, hydrazine has a lone pair because we have two nitrogen atoms, if you see. One of these is able to give an attack directly on the carbonyl of the ketone carbonyl of the ketone function, and not on the carbonyl of the amidic function. Why? Because only the ketone, the carbon of the ketone has a partial positive charge, while the amidic carbonyl, no, because if you remember, there is the delocalization of the lone pair of the nitrogen of the amido function on the carbon. So only the carbonyl of the ketone can be attacked by hydrazine. And the result is the formation of a hydrazone, the Schiff base, if you remember. Ctrl C, Ctrl V. Questo. Here we have the formation of nitrogen hydrazone. The Schiff base with the loss of a water molecule. After several steps, we have also a loss of the, a loss of the hydrazinic group as nitrogen. Nitrogen is a gas. So we have the reduction of the carbonyl group by using hydrazine, because we have the formation of nitrogen as gas. So this means that we have the reduction, remain only the CH2 in this position, and so we have the formation of this compound. Tac, 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 tac. Here you see we have 2 hydrogen. At this point, you see the last step is just an hydrolysis of the amidic bond to release the side chain of the acetic acid residue. So the last step is an hydrolysis. So we have here, we can have this type of reaction with the formation of the acidic group, of the carboxyl group. And this is diclofenac. So the starting point is represented by diphenylamine. Diphenylamine is able to give an attack to the activated oxalic acid. We have the formation of the first amido group, and then intramolecular Friedel-Crafts reaction, we have the ring closure, formation of this 5-member ring with 2 carbonyl groups, but one is an amidic group and the second one is a ketone. Only the ketone is able to react with the hydrazine to give hydrazone, double bond, Schiff base. After several steps, we have the release of nitrogen gas to give the reduction of this carbonyl atom. And then the final step is an hydrolysis of the amino group to release the free acid function. Have you any questions? Is it clear for you? Questions, organic chemistry questions? No? At home, have you any questions?
No question, Prof.
Okay. So we can see again the slides. This one, okay. We can comment together this reaction. Once again, you see oxalyl chloride. The lone pair is able to attack the activated carbonyl to give the first amino group. F dot C dot means a Friedel-Crafts reaction. So we have the formation of the 5-member ring. Wolff-Kissner reduction with the hydrazine to give the reduction of the carbonyl of the ketone function. Hydrolysis, the last step. Here you see how is it possible to reduce the hydrazone to carbon. You see a lot of different equilibrium, but the last step is represented by the formation of nitrogen as a gas. And so you know, in this way, we have a shift of the whole equilibrium towards the right. So for this reason, it is possible to have this type of reduction of the ketone function. these steps are not requested during the exam. I am interested only in this step, okay? You can show me from the carbonyl, we have the CH2 with the hydrazine, and so because there is the formation of nitrogen gas, but these different steps are not requested. Okay. Fourth class of anti-inflammatory agents. We have seen the class related to acetic acid, in particular diclofenac, aryl acetic derivatives, or heteroaryl acetic derivatives, indomethacin, sulindac, tolmetin, ketorolac. Now you can see how it's possible to have a residue of the propionic acid. So an homologation, we have an introduction of a second methyl group on the acetic acid residue. Here in the class, you can find the best seller between the anti-inflammatory agents after aspirin. In particular, you see ibuprofen, commercial name is Moment, flurbiprofen, phenoprofen, ketoprofen, naproxen. Why there are so many compounds in this class? Because every company wants to have their own product in this class. So if like the cars, you know, Toyota, Fiat, Volkswagen, the same shape, not the same engine, but more or less the same shape. Here is the same situation, the same shape, the same function, but please, the same function, propionic acid residue. They change only the side chain. What means ibuprofen? Ibu means isobutyl. You see here in para position, you see the residues of isobutyl, 4 carbon atoms. And isobutyl in English is indicated as Ibu. So Ibu means isobutyl. Profen means propionic acid. So all these compounds are characterized by the residues of propionic acid. If we see carefully this type of molecules, we can see that there is a chiral center, a chiral carbon atom in each of these compounds. But they are sold as racemic mixture. The FDA, the American Federal Drug Agency, says that if we have 2 enantiomers only the active enantiomers can be sold on the market. Only the most active, because the other one can be considered as a toxic compound because perhaps it has no activity, but it should be metabolized by liver. In this case, we have a mixture, a racemic mixture. Why? Because it was observed that in vivo we can have a racemization, in vivo racemization. So we know that the most potent isomer is the S isomer, sinister, but on the urine were detected a lot also of the other isomers. So in this case, when we have an in vivo racemization, it is not worth to make a separation, to separate the two isomers, because you know it's very expensive, this step, time, the requested time, requested solvents, and so if possible, in this case it is possible, you can find the racemic mixture on the market. Only naproxen makes an exception. Why? Because some patients have not this type of in vivo racemization. So company decide to introduce this compound as in an enantiomeric pure form. So for this reason, naproxen is more expensive than the other compounds, because you have the pure enantiomer of the S form of naproxen. Naproxen cannot be racemized, and so in some patients, and so it's better to know exactly the concentration of the active compounds administered to the patients. And so naproxen is sold in an enantiomeric pure form. The only one. All the other are in racemic forms. Once again, these compounds are anti-inflammatory, have anti-inflammatory, antipyretic, and analgesic activities. Naproxen is 20 times more active than aspirin as anti-inflammatory. The ibuprofen, phenoprofen are more or less the same. They cause less intestinal discomfort, intestinal gastric problems, less intestinal gastric problem than aspirin. They are less toxic against stomach. Once again, they interact with the acidic group with arginine 120. Enantioselectivity, S major than R, okay. They have also inhibition of activity on leukocyte migration. Okay. What about ibuprofen? the most active form is the dextrorotatory enantiomer, okay. But we are metabolic inversion, as I told you before. There is a new term that you can find in the literature about these compounds, eudismic ratio. What means eudismic ratio? In this case is equal to 160. Eudismic ratio is the ratio between the activities of the two enantiomers. S over the R. So in this case, we have a difference of 160 times of activity between S and R. But as I told you before, we have a metabolic inversion, so we can assume a mixture of the two enantiomers, because in vivo we have a racemization of the S in R. So we can use the mixture. Eudismic ratio is the ratio of activity between the two enantiomers. This is the definition of this term. Naproxen 1 again is the only one sold as a pure enantiomer. It is the most active of the class, but less than indomethacin. Indomethacin represents the reference point, the most potent, but also the most toxic. Please remember. Phenoprofen, okay, more or less the same, nothing new. Ketoprofen is another one, very, very common in as cream against pain and inflammation of legs, of fingers, sport accidents normally. Fifth class, Pirazolone. You see the backbone of this class. 3,5-pyrazolidine-diones. This class is not so famous because some of the prototypes of this class are very toxic. And so there was in the past an example of this class on the market, but now is no more present. So we have only an historical interest of this class. You see here the exponent, the prototype, phenylbutazone. And if you see this chemical structure, we can make a question. Where is the acidic function in this class? Because if you see, no carboxylic group are present on the chemical structure. So where is the acidic function? You have to see carefully the chemical structure, and you see here in this point there is a proton. Proton located on a carbon between two carbonyls. you see better in this picture. You see the proton, the acidic proton, because we are between two carbonyls, and so if we have the loss of the acidic protons, we have the negative charge can be delocalized on the two carbonyls. But as I told you before, this class is not interesting. There is one compound in therapy which derives from phenylbutazone, but it is not used as an anti-inflammatory, but used as anti-gottosis. It increases the elimination of uric acid in urine. There are some people which are not able to metabolize the DNA bases that we can assume with meat from animal sources. And in particular, they have a recovery, a reuptake, a reabsorption of a uric acid at the renal level, in kidneys. Uric acid inside the body can represent, can make a strong inflammation of the foot finger, because uric acid in body crystallized and the gravity attract these crystals inside the foot fingers, and so we have a strong inflammation of the foot fingers. If you want to avoid this type of effect, we have to increase the elimination of uric acid at the kidney level. We can assume a lot of water, okay, but in this case, it is necessary to use a compound with the great affinity with the recovery system of uric acid at the renal level. We say uricosuric activity. And sulfenpyrazone, you see the same backbone of phenylbutazone, has this type of activity. Sulfenpyrazone has a strong affinity for the reuptake system at the renal level of uric acid. So in this way, we can block the reabsorption of uric acid that can be eliminated inside the urine. But sulfenpyrazone is not an anti-inflammatory agent, so it's another class. So in this class, no interesting compounds. Now, in the past perhaps, but no more now. Okay. Last class. Okay. So this class, it is very interesting, and perhaps it's better if we describe this class next time, because it's long and it is one of the most recent class of anti-inflammatory agents. So I think it's better if I will finish this point Monday in the afternoon. And so, in fact, you can see that we can find some COX-2 selective agents in this class, so it is interesting to describe this class next time. Okay, so have you any question at the moment? No? No more questions? Okay, dear students, so we'll see you next time Monday afternoon, and then the end of the lesson. Just a moment. Okay, we can